Okay, we got homework 3, part D. The questions being show how the Maxwell-Stefan equations expressed as difference in component velocities is equivalent to the Maxwell-Stefan equations expressed in terms of molar fluxes and then molar diffusive fluxes. And then 2, for ideal mixtures with reference chemical potential as the pure state, show that the Maxwell-Stefan driving force for a 1D problem simplifies to just the derivative of the mole fraction with respect to a coordinate direction. Show how the equation simplifies the Fick's law and what is the relevance of it. So to get started, I just have the equation here. I put Stefan Maxwell, but it should be Maxwell-Stefan. Oh well. But here we have our mole fraction I times the gradient over our RT, which is a constant, and our temperature is equal to the summation from 1 to n when j is 1 of mole fraction of, this should be an I, of our I times our molar flux of j are subtracted by our mole fraction of j times our molar flux of I all over our concentration times our diffusion constant. So we're going to hop right in and show how we're going to start with our molar flux in terms of molar fluxes. So what we're going to do first is we're going to just simplify this equation, and we're going to have our left side of our equation is also known as driving force, which is in terms of di, but I'll also write driving force. So we're going to have our driving force is equal to the summation times our top value. So that's just basically simplified down. And then what we would want to do next is bring in our velocities. So this numerator can be rewritten, and we'll just have our driving force is equal to our summation, which is going to be equal to our x, which is our mole fraction of I times our mole fraction of j, and then multiplied by the velocity subtracted. And then that will be all over just dij. Sorry, see. Okay, so now what we want to do is basically just relate these two terms that we have here. So our velocity term and our just simplified MS version. So we're going to have to multiply by c. Oops, sorry, this should not have c yet. We got to do that later. I got ahead of myself. So we're going to have to multiply by c because on here on our right side we have no c, and on our left side over here we do. So in order to get that, we're going to have to multiply our velocity equation by c. But to do that, we need to put it in the numerator and also the denominator. So we're going to have di is equal to the summation, and we're going to have to multiply by c, so we'll get c times our xi times, times our 2 molar, I keep forgetting mole fractions, geez. And then that's going to be multiplied by our velocity, change in velocity. And then that will all be over c times our dij. That looks like a d. Or dig. Okay. Seems good. And finally, what we're going to want to do now is just rewrite this, but with multiplying in our terms. So once we multiply in our terms, we're going to have the same on the denominator, so I'm just going to write that now, and then on our top we're going to have the xi will stay, velocity j, and then subtracted by ci, just the same but the opposite. And knowing that we know from previous videos that n is equal to vc, we can add individual components and find their, like, what we're looking for. So once we use our n equals vc, we're going to end up getting summation will stay, excuse me, so all we did in this step here was just take v times c, so take this component. Since we have our two j components, we can just rewrite that as nj, and then same with here with our ij, or our in and I. So what we have here looks very similar, or looks very familiar, but we have to do one more thing to finally get to our answer. So now we just need to show our molar diffusive fluxes. So this is going to be the answer to our first one here, our molar fluxes, but we still need to get to our molar diffusive fluxes. So we're going to move on to that part. And then another equation that we know from previous videos and classes is going to be n of component I is equal to j of component I plus x component I times n, but we need to carry our c throughout the entirety of this problem because we've been dealing with concentration. So we're just going to add that c in there. And then finally, we're going to just substitute in another value for n, just as we did above. So let's just write out this big thing. So we're going to have di equals the summation. That's the only thing that hasn't changed this time. And we're going to have a long fraction. We're going to have xi, I have to go up, there we go, ji plus x I c n, and then minus xj, jj plus xj cn, didn't even have a long enough fraction, and then that will just all over be cdj ij. And then now all we need to do is just multiply in our xi and xj. So let's multiply that in quick. So together. So we're going to be left with there we go. And then we can see that this will cancel, this will cancel, go to zeros. Not that I really need to write 0, but we'll go to zeros, and then, oops, sorry, I forgot our denominator, which stays. So we're going to be left with so this is our value that we're left with, so I'll box this up. Still good. Okay, and I'll simplify this here. So these will be our answers to part 1. This first one being our molar flux, and this bottom one being our molar diffusive flux. So that looks good. So now we're going to move on to question 2 and work on that. Okay, on to part 2. Here we just have our question, I should probably read, is for ideal mixtures with reference chemical potential as the pure state, show that the Maxwell-Stefan driving force for a 1D problem simplifies to just the derivative of the mole fraction with respect to coordinate direction. So I just copied down our Maxwell-Stefan equation and our values, or our glossary, I guess if you want to call it here, and I added our standard state for our gradient on it too, and here I just have our gradient at I is gradient of I is equal to our standard state gradient of I plus RT natural log mole fraction I. So it kind of explains our standard state a little bit, so let's get into it. So we're just going to start with our Maxwell-Stefan equation. But first we need to remember in previous videos we've done that our gradient of our mu I is equal to our derivative of mu I over our dz, our length. So now all we have to do is use this and plug in our standard state. So we're going to be left with, we're going to have to do a derivative, so we're going to need that d. Well, we're also going to need to plug in our mu I, so mu I naught plus x. That'll be all over dz, I believe, yeah, dz. And then we're going to have to take the derivative of the top. So a derivative of a constant is 0, so that's going to be 0. Derivative of RT will stay just RT. And then taking the derivative of a natural log puts it over in the denominator of a fraction. So we're going to have 1 over xi, and then we're going to have to keep our d mu I over dz. So, oops, that looks good. Oh, oops, hold on, gotta get my camera back. There we go. This is not mu I, this is xi, or our mole fraction I. And then that is equal to above, so our gradient mu I. So now we plug this into, we'll plug in, this mu I, that looks really bad, but that will take this spot in our Maxwell-Stefan equation. So we're going to add that quickly. Okay, let's do that. So we're going to have our xi and then plug in our fraction, so we're going to have RT 1 over x dxi dz over RT. I'm just going to keep that. And that will be equal to our summation. Oh my gosh, where's my handwriting? Summation and j equals 1. And then xi and j minus xj and I. Good. Looks good. So when I was writing the list, you can notice these cancel, all those cancel, so we would just be left with dxi dz on the left. So there we go. So now we're left with this expression, which just means that our chemical potential at I is equal to our chemical potential of our standard state, I, which is really good. to further simplify stuff, kind of explain what we're doing in that equation, or that problem. So this would be kind of our answer in the explanation I just gave for 2. So we're going to move on to 3, which is show how the Maxwell-Stefan equation simplifies the Fick's law for a binary mixture. We're just going to do a new page. Okay, so we've just kept been writing the summation down further and further, like that we just kept doing, so we're actually going to perform the summation now. So we're going to have our di, which is equal to, I have to need that, I already forget. So we're going to be, our di is going to be equal to x1, or j, we're not going to be using the n version, we'll be using the j version, but it still works, or I like can reference it still. x2 over, gosh, please just, oh my, cdi, or 1, 1. I don't know why I wrote that as a 2. Okay. I'm out of it today. So all of this is just going to equal 0 for our first area summation, but we still need to add our second part, because we're going, since we have a binary system, we need to do it 2 times. So we get x1 j2 minus x2 j1 over cd1 2, and now we just have to add our driving force in, which is going to be our derivative of xi, or x1 over dz, as we defined multiple times now. So we're going to do dx, not xi, x1 over dz is equal to x1 j2 minus x2 j1 over cd1 2. Cool. And then since we know this is a binary mixture, we can get we know that y2 is equal to 1 minus y1, and we also know that negative j1 is equal to j2. So that's going to help us further simplify these. So now we're just going to take these values here. So, or sorry, not y2, this should be x2. So we know that these values, geez, I wrote y's. Why did I write y's? x1 is equal to 1 minus x2. So we know we can simplify for x1, we'll just plug in x2. And for the j's, we're just relating terms here, basically. So we'll be left with x1 over dz is equal to x1, and then we'll have negative j1 minus 1 minus x1 j1 over cd1 2. And then we gotta multiply terms in, and we'll like multiply these in. So we'll be given negative x1 j1 minus j1 minus, or plus x1 j1, which these two will cancel out, so you'll just be left with j1 in our numerator, and then in our denominator nothing changes. And then when we rewrite this term, we'll get Fick's law, which is just j1 is equal to negative cd1 2 dxi over dz. So this is equal to Fick's law. So that is basically how we get from are Maxwell-Stefan to Fick's law, and this only works for the ideal binary mixture. So, to kind of go over for what's the relevance and application of the Maxwell-Stefan equations, let's scroll down a little bit. So, these, as we can see in like mainly 2 and 3, is that the Maxwell-Stefan equations, when you use them binarily, it makes comparing mixtures easy, even in liquid, vapor, multi-state processes. So it helps you kind of get a bigger picture of these relationships.